Next speaker today. Next speaker today is Professor Bartosz Malman from KTR, who will speak on the smooth functions in the Branges-Rovnyak space in the connection with subnormal operators.
Thank you very much for the introduction, and I thank the organizers, of course, for the invitation and letting me have this opportunity to speak. In general, I want to thank the organizers for this, for the tremendous effort that is being done here for a half a year program on our field. And I will want to contribute to this with a talk based on some work that I've done in cooperation with my dear friend and previous colleague Adam Limani from Lund University. This work is inspired by some previous work I did with Professor Alexander Alman, also from Lund University, who has been my doctoral advisor a couple years back, 2 years back. So with Adam, we studied the following general questions, which they fall under this general research theme that we see on the screen. We will soon specialize to the Branges-Rovnyak spaces, but I want to mention a couple of words about this problem in general. So we take a class of analytic functions y that we will be working in the unit disk of the complex plane, and as well we fix some class x, some analytic functions enjoying some extra regularity or maybe some other desirable properties, and we ask ourselves the question whether there exists some non-trivial function f that is in this regularity class x in our space y. If yes, then we can of course ask further questions if there are many of them, and perhaps if y carries a topology, we can ask if these good functions in X are dense. This question makes sense if the members of y are not easily identifiable. So clearly this makes sense for the spaces that have been talked about during our conference, the model spaces, certainly the Branges-Rovnyak spaces, especially in the extreme case, but also in various other contexts. And I want to mention specifically one which will be important for our purposes, and this is also a question that we have been exploring with Adam, and it's related to transforms, to Cauchy transforms. So I will not define these objects because I will not be speaking about them too much, but the work of Khrushchev, a very deep work of Khrushchev on the something that he calls removal of singularities of Cauchy transforms, as a matter of fact, will play a crucial role, background role in background. But so I will not be speaking too much about his work, but it is crucial in our background development. And what he studied is the following. So he takes a closed set on the unit circle, and he asks the question: what geometric properties must this set have, must this closed set possess, so that we can place a mass on it, a measure, a positive measure, such as this Cauchy transform becomes a function with some desirable properties, for instance, has continuous extension to the boundary, or perhaps some more smoothness. That question and his work will be highly relevant, and we will bring up examples from his work. So there will be some redundancy in the slides. We have been talking about the Branges-Rovnyak spaces for now a couple talks. So let me say the following: we will be studying the density of smooth functions in the Branges-Rovnyak spaces, or at least the existence of some smooth functions in these spaces. And by a smooth function, I mean the following. I will be using this phrase repeatedly, and I mean a function which possesses the kind of regularity which is a little more than perhaps continuity up to the boundary. So we should think that its derivative perhaps has a derivative of a function has a continuous extension to the boundary. So some sort of a C1 boundary, the functions with boundary values of C1 smoothness. The Branges-Rovnyak spaces have been thoroughly defined. In other talks, I will just say that I will the defining function B I will often call the symbol of the space. So now here is another redundancy, although on this slide there is a very important quantity which I'll get to. So our question is the following: for which symbols B, or what kind of properties must the symbol B have such that HB possesses a dense subset of functions with some prescribed degree of regularity, right? So some smoothness class. And well, here we have heard that the theory bifurcates in two directions. We have this classical dichotomy, which is implemented by the following quantity. I call it delta, and this is a weight on the unit circle. We have heard of it before. The logarithm integrability of this quantity on the entire unit circle, and I stress this on the entire unit circle. If this is so, then Saracen proved long ago, at least in the 1980s, so that the analytic polynomials are dense. We have heard about this in Dan Timothy's talk. Nevertheless, on the slide, the equation 2, the object, the delta, that I put the name, the weight that I put the name delta on, this will be a crucial object. Here is another redundancy, and then we will actually get to something I think new. So in the absence of the condition of the logarithm integrability of this weight delta, so in the so-called extreme case, Alexandru has already mentioned the theorem that we obtained a couple of years back when I was guided by him during my PhD studies, and we showed that the functions extending continuously to the boundary are always dense in the Branges-Rovnyak spaces. So it's an elegant result which I like. And in this talk, we want to go further. We want to exchange these functions from the so-called disk algebra, which extend continuously to the boundary, to some spaces of functions with more regularity. It turns out that this question is interesting in a different way. So as for this result from 2017, we need no conditions on B, and this is just a general theorem on the Branges-Rovnyak spaces that such disk algebra functions always are dense. If we ask, as a matter of fact, only a little bit more regularity. For instance, if you ask, can I approximate or can I find a function with continuous extension, but even something maybe benign like Holder type conditions on the modulus continuity. Already this question is completely different from this, and we will actually need some conditions on B. And in this talk, I will present conditions which guarantee such approximations for not only for functions such as the Holder class functions, but we will I will define precisely which kind of regularity classes we'll be working with shortly. But also we will explore some conditions on which prohibit such approximations. And so where are we going with this? There will be more or less two parts in this talk. And in the first part, we will connect this question of these smooth approximations in HB spaces to a different theory, somewhat well-established theory, and it's a theory of certain Hilbert spaces of analytic functions, which lie kind of strictly in between the classical Hardy spaces and Berman spaces. So it will be in a setting of spaces which exhibit, which lie in the Berman spaces, but in some sense exhibit Hardy space properties. In particular, this connection will lead to a study of invariant subspaces of a certain operator defined on these spaces, on these spaces that lie in between Hardy and Berman spaces, and the possibility of smooth approximations in HB spaces will be encoded in the properties of the operator of this operator and defined. This connection will so the HB space theory will benefit from this connection because actually these spaces I'm about to define, there's a deeper theory that a lot has been done, and with Adam we have been trying to push it further in the directions of where we can apply the results to HB spaces. So the operator which we'll be studying, it belongs to the class of the so-called subnormal operators. Essentially, a subnormal operator is an operator which is the restriction to an invariant subspace of a normal operator. So we have two Hilbert spaces H and K. K is a bigger space than H, so H is contained in K. And if we have an operator N, which is normal on the bigger space, and perhaps it has an H as an invariant subspace, then the restriction of N of the normal operator to the invariant subspace is the definition of subnormal operator. I think they have been defined by Paul Halmos long ago. There is a typical example of these operators, and it is constructed in the following way. So we take a mu, which is a completely supported measure in the plane, and we consider its usual L2 space of this measure mu of measurable functions. We construct the closure of the so-called analytic of the analytic polynomials in L2 of mu, and we will call it P2 of mu. Now, the set of analytic polynomials is invariant under the operator of multiplication by the coordinate function, which I will refer to this as mz, and this multiplication takes a function fz to the z times fz, so a multiple of the coordinate function. This is a typical example of a subnormal operator in the sense that under some natural assumptions, any such operator, for any such operator, you can find a measure, a completely supported measure in the plane, such that this operator S is unitarily equivalent to this shift operator. So that you should just put some very natural conditions like cyclicity. These spaces have been thoroughly, well, these operators have been thoroughly investigated, and these spaces P mu as well, among others by Saracen. By Scott Brown was the one who proved the existence of invariant subspaces for this class of operators. Thomson did a very deep work on so-called bounded evaluations, although I will not be speaking about them in my talk. And there is a very relevant work for myself and Adam by Alexander Aleman, Stefan Richter, and Carl Sandberg, and they were exploring PT mu when it in principle is a space of analytic functions, and they were investigating function theoretic properties of this space. So now I want to start do the work to prepare for the theorem which will connect these two theories, the subnormal operators and the approximations in HB spaces. So here is a principal construction of myself and Adam. For a given space HB, and so we take a symbol B, and we will give ourselves a parameter alpha, which is positive. We will construct a measure, a mu. The measure depends on the parameters alpha and B, and it is supported on the closed unit disk, and is given by the following formula. So basically, we have a piece on the open unit disk. The dA stands for the area measure, and we weight it with this following weight, which is essentially a standard Berman weight. But this measure will also have a piece on the boundary. dm stands for the Lebesgue measure or arc length measure on the circle on the boundary of the unit disk, and we weight it with delta, which is this quantity which implemented the HB dichotomy in principle. So here we encounter it again. This will be a principal object through the entire talk. So here I draw a little bit of a picture of this, and then we have the unit disk and the weight inside, which is the Berman weight, and then we have the boundary here. In fat blue, I have drawn the place or the places on which the delta weight lives. So in fat blue, we have this let's say the carrier set of delta or the support set of delta, and in the thin one we have there is no mass. So I will have a couple of pictures like this when I draw some geometric concepts that will be relevant for us. I said that we'll be studying spaces of analytic functions in between the Hardy and the Berman space. Now, what I refer to is that we'll construct this PT mu space from these measures, which kind of look, you see, they have one piece on them, which looks like the measure that basically defines the Berman spaces, right? The Berman spaces, you integrate, you have an area integral over this weight, and then maybe a weighted Hardy space on the unit circle. But in fact, I was a bit bold when I said that we will be studying the spaces of analytic functions. This PT mu space that we will construct from this measure might not very well not be a space of analytic functions. So it might be so that we take the closure of analytic polynomials in the L2 of a measure like this mu, and something wrong will happen. So we will obtain a space which has it cannot be identified with space of analytic functions, but the concept will be crucial for us. And in fact, for the measures of this form, one can see that this PT mu space we will be able to identify it as a space of analytic functions. This is nothing that I will prove, and there will be not so many proofs in this talk, but one can see that the possibility to identify each element in this PT mu space with an analytic function is equivalent to the operator theoretic property of this MZ shift operator being completely non-isometric. And by this, I mean an operator is completely non-isometric if it admits no invariant subspace on which MZ acts as an isometry. In fact, if such an invariant subspace exists, then more or less it will, that's an imprecise claim, but it will somehow live on the boundary. All right, so now I would like to present our, so to say, cornerstone theorem with Adam on the connection between the two theories, and which lets us then encode this possibility of the smooth approximation with the properties of the operator MZ. So the connection will be expressed in terms of two function classes. The first one is X alpha, and this function class is our smoothness class, so to say. So we will be we want to approximate by this function. We put this function class because it's easy to work with. It's a Hilbert space, and it consists of functions. It depends on the parameter alpha. Remember, alpha is some positive function, some positive number, and we have the function in the space for growing alpha have Taylor coefficients which decay faster and faster. So this is a simple way to quantify some sort of a regularity in some sort of regularity of the functions in the space. In particular, if alpha is sufficiently big, then it is easy to see that these functions in this space will have some numbers of derivatives extending continuously to the boundary. So these are our good functions. For alpha is equal to 1, we have the Dirichlet space. But we can think of alpha as big, even for small alpha, there's some interesting conclusions that we can draw. The other function class that that we will need to introduce is the usual Smirnov class of the unit disk, which is those functions which have a factorization in terms of the usual outer function. So you synthesize the f from 3 factors. It's a Blaschke product outer function and the singular inner function. This will be the important one. So here is our theorem, right? This is the theorem that translates the approximation problem to this theory of subnormal operators in PT mu spaces. We have the following object here. B is the symbol of our space. Theta is its inner factor. It will play an important role. And mu alpha B is the connecting measure that I constructed here. The following statements are equivalent. The first statement is the density of this smoothness class in our HB space. And the second is as follows. So the operator MZ, the shift operator on the PT mu space, should be, first of all, completely non-isometric. That's a necessary condition. As I explained earlier, being completely non-isometric, this means that PT mu is genuinely a space of analytic functions. And if it is a space of analytic functions, then the rest of the text here makes sense. So MZ should satisfy the following property, which we call P, and we call it the property P for permanence, which will be clear soon. So if F is a function contained in the, so F is a Smirnov class function, and it is contained in the smallest MZ invariant subspace containing theta, the inner factor of B, then we can divide F by theta without leaving the Smirnov class. In other words, F has theta as a factor. And this permanence property, we call it property P for permanence because of the following. So if the smallest MZ invariant subspace containing theta is, of course, it's the closure of the analytic polynomials times theta. So if F is in this subspace, there must exist a sequence of polynomials times theta, which converges in the PT-mirrored norm to F. And the relevant property we're asking for, that is needed for these smooth approximations in AG, is that this theta factor gets passed on in the limit to the limit function, and that's what we refer to as permanence. Now, some comments regarding these two assumptions. One more comment again about completely non-isometric assumption, and then the property P. First, the completely non-isometric assumption. I already said that it's equivalent to PT mu being a space of analytic functions, but the relevant property of the measure mu, which ensures this, being PT mu being completely non-isometric, is qualitatively the following. If a sequence of polynomials converges on the disk to 0, then it converges on the circle to 0 as well. And more precisely, I mean convergence to 0 in the L2 metric of the restriction of mu to the disk and respectively to the circle. So this has been called by in some literature as resembling some sort of an uncertainty principle, where you cannot be 0 in one place without being 0 in the other. And such convergence has been thoroughly investigated and characterized by Khrushchev. And as a matter of fact, this study of this principle, it is tied to this removal of singularities of Cauchy transforms that I mentioned earlier. Khrushchev made great advancement for us for our understanding of this phenomenon, and his examples will be very relevant later on. So the second comment again about the second property, this division property P. So more or less, this property has appeared already implicitly or explicitly, more implicitly in other approximation problems in the Branges-Rovnyak space, namely in my work with Alexander on the density of functions with continuous extensions. But also it has appeared in the work of Alexandrov in the corresponding result for model spaces. So with Adam, we have somehow formalized it. It is somewhat similar to this classical F property, where you can divide out inner factors of functions without leaving the space, but it is slightly different. Now, the division property is it's trivial for the Hardy spaces, right? There clearly, I mean, the inner factors are passed on. The non-trivial case, already in the Berman space, we have something non-trivial happens, and in the Berman space, the functions with the property P, with the permanence property, have been characterized. This is more or less the work of Boris Korenblum and James Roberts, and it turns out that the inner functions with this property are precisely the ones which have singularities carried by so-called Beurling-Carleson sets. And I will define Beurling-Carleson set in a bit. So by singularities, I mean the discontinuities on the boundary. So each singular inner function, well, of course the Blaschke factors as inner functions, they always have the division property, but we are focusing here on the singular inner functions. For this, the property is non-trivial. So such a singular inner function theta is defined by a positive singular measure which is placed in the unit circle, and the discontinuities lie. The discontinuities of theta then lie in the same places as the mass of the defining measure. All right, so now I've presented the main theorem, the main connection theorem, but that's an abstract theorem, but we would like to extract something from it, right? So now I claim that this theory of approximation will benefit highly from this connection. So we will give some concrete results, some quantitative, well, I will give some qualitative conditions on B, which prohibit smooth approximation in HB. And there will be 3 of them. Then once this is done, well, some of them will be qualitative, some of them will be more geometric. But then after that is done, then I want to show that with Adam we are we do not have an if and only if theorem, but we are kind of on point, close to at least. This if we avoid these 3 principal obstructions, then we can show we will be able to construct a very large class of extreme HB spaces in which smooth approximations are possible. So I promised I would define the Beurling-Carleson sets. We will not go in depth on these sets, but the definition I think should be in place. So we take a closed set E of the closed subset E of the unit circle, and like E could have measure 0, but it could have a positive measure. As a matter of fact, we will need to use both types in our presentation. Being a closed set, its complement can be written as a union of open circular arcs. Now, if these circular arcs are spaced on the circle in such a way that this quantity here, and by a bar AK bar I mean the arc length of AK, if this quantity is finite, then we call such a set E the Beurling-Carleson set. These sets are related. They are they are related to smooth functions in several ways. They are both the 0 sets on the boundary of smooth analytic functions, but also they are related to constructions of these smooth Cauchy transforms of Khrushchev. I do not want to go in depth of these sets, but I thought I'd draw a little bit of a picture to demystify this quantity a little bit. So I have 2 8-point sets here, 8 E and E prime, 8 blue dots, and here and this one we have equally, they are supposed to be equally spaced, while here they are in more disorder. And this quantity, if you compute it for the 2 sets E and E prime, then it will be bigger for the one here on the left. And as a matter of fact, if you space them equally, like I try to do here, then this quantity should be maximized among all 8-point sets. But we will not go into the geometry more of this. Finally, I want to present these 3 principal obstructions that we have found that prohibit approximations. So bad qualities of the symbol B. First is a bad carrier set E of this weight delta, right? So here is the weight delta. The set E is the carrier, right? It's defined up to set of measure 0 if delta is only measurable, not continuous. And irrespective of other behavior of delta, irrespective of how this looks, but only knowing that E is the carrier set, this can already destroy smooth approximation. So there exists such a set E, such that, and here we actually prove a little more with Adam, is that the intersection with any smoothness class, that this alpha can run over, this could be any positive number. Here in this case, I forgot to write it on the screen. So the HB will contain no non-zero function from a smoothness class like this, whenever B is an outer function and the carrier set of the delta is this set E. So irrespective of how else B behaves, it's only the structure of the set E that plays a role. And we derive this from our main connection theorem through together with a very, very deep result of Khrushchev, who worked on basically on PT mu spaces, although in somewhat different language. And he proved that there exists a set E, and that this set E is such that it contains no Beurling-Carleson sets, which are defined previously, no Beurling-Carleson sets of positive measures. So it's something very weird. And then in that case, he proved that, that the PT mu space, or at least his result implies that the PT mu space of our connecting measure splits into two pieces. One piece is the Berman space, basically. So this piece, this is precisely a weighted Berman space, and I forgot the alpha here. The alpha should appear on the top. But there is another piece, and it's the piece on the boundary. It's an L2 space of the weighted circle. This happens for any alpha. Of course, now through this connection theorem, we should remember that smooth approximations are equivalent to, in this PT mu space. Well, it's with the P, we have the P property, but first and foremost, MZ operator should be completely non-isometric. Well, this piece is certainly an invariant subspace of MZ on which MZ acts as an isometry. So the smooth approximations cannot happen for B's satisfying this property. And in fact, if it goes a little bit more, becomes a little more technical, and I can show that not a single such function can exist. So the first principal obstruction is a bad carrier set of the weight delta. Now we have the second principal obstruction, which is the size of the weight delta itself. So in the previous slide here, we had this was only related to its to the structure of the set E. Nothing was said by delta. But even if delta is carried, supported by a very nice set, still something else can go wrong, and delta can be too small. And here there is another example which we found. It is an example of Wahlberg. He constructs a measure d mu, which is the sum of the area measure on the disk, on the open disk, and a certain weight here, which I will call delta again, which is bigger than zero almost everywhere. It's positive almost everywhere on the entire unit circle. So in principle, the carrier set here of delta, this set E, is more or less, well, I mean, it's up to set of measure zero, the full circle, right? So it's certainly a good set, but still this happens. Still the splitting occurs. And using this example with the main theorem, with the main connection theorem, again, we showed that there exists a B now, which is less than one almost everywhere on T. And yet again, smooth approximations are impossible. And as a matter of fact, there is not a single function, non-zero function from this smoothness class in the HB space. So such examples. In Wahlberg's example, this will be somewhat relevant for what I will say later. The weight, it's non-zero almost everywhere, but it is at the same time very small everywhere on T. So what I say is, I write a bit imprecisely here that the logarithm of delta is nowhere integrable. And what I mean by that is that if you take any arc on the unit circle and try to integrate the logarithm of delta, the logarithm of the Wahlberg's weight, then you get minus infinity. So the second obstruction is the delta, the weight delta is too small, or otherwise B is too close to 1 in modules. These two obstructions had to do with the outer factor of B. There is a third one, which relates to singularities of the inner factor of B. And this is the discontinuities of the inner factor of B on the boundary. And it turns out that, well, they can be in wrong places. And I will soon be precise about this. We take our symbol B again, and we take out its inner factor. Now, the inner factor is, as usual, factored into a Blaschke product and a singular inner function defined by a singular positive measure nu. Now, that's not good enough for our purposes. We need to refine this factorization we need to split nu into two pieces, and I call them nu C and the nu K. Out of these three factors, which I will soon describe these two, but the first two, the Blaschke product and this one, nu C, these are benign for approximations, for HB approximations. The critical part is this one. And let's see, the second one here in the middle, it's the corresponding measure nu C, and we write C for Carleson because this measure lives on a countable union of this Beurling-Carleson sets of measure zero. And as a matter of fact, I mentioned earlier that this function then has this singular inner function has this division property P with respect to the Berman spaces. And well, these PT mu spaces that we are interested in this in this setting, they are contained in the Berman spaces, which means that basically this factor will always satisfy this permanence property, and we don't need to worry about it. It's benign. It has no relevance. The other one is critical. However, we call it nu k for Korenblum, and this is the part of the measure nu which vanishes on Beurling-Carleson sets of measure 0. So it's a weird measure. It has been shown at least by Korenblum, but also by James Roberts, that the singular inner functions defined by such measures, which vanish on BC sets of measure 0, they are cyclic vectors for the shift on the Berman space. And here I mention Roberts as well because so James Roberts has done a very important work on these measures which vanish on BC sets. He has a very useful decomposition theorem for them, which I will not go into details, but I wanted to mention him because, in fact, with Adam, when you dig down into technicalities, we use his his result a lot. Now, so of course, an inner function which is cyclic, it could never satisfy this permanence property, because a cyclic inner function, there will be a sequence of polynomials times this inner function, which will converge, say, to the constant function 1. And clearly the inner factor has not been passed. So for cyclic inner functions, permanence property could never hold. That's why it's interesting. It was interesting for us to study cyclic singular inner functions in PT mu spaces. And with Adam, we have this following result. So this is a purely PT mu space result. We assume that we have our measure, connecting measure as usual, and the PT mu is a space of analytic functions, so completely isometric. If F is, here is a little technicality, if F is the closed support of delta, so delta lies here, and the technicalities here before we were talking about the carrier set, so the carrier set where delta is non-zero, no closure. If F is the closure, but it's basically the blue set here in the picture, and nu k is a singular measure, and it assigns no mass to this Beurling-Carleson sets of measure 0, but also it doesn't assign any mass to the support of delta. In other words, the singularities of this singular factor, they lie outside of the support, so I wrote them in red here. Then we use this Roberts decomposition that I mentioned earlier, and we proved that S nu k is a cyclic vector for the MZ operator on PT mu. Now, the implication of this result to HP spaces is the following. It's an immediate corollary. And together with this main theorem, we know that theta has to have, for smooth approximations in HB, we have to have theta satisfy this permanence property, this passing on the inner factor. But well, if this we call it the Korenblum part, if the bad part, the critical part of the measure places mass outside of that support, well, then it's easy to see that that theta will have a factor, will have a singular inner factor, which is a cyclic vector for PT mu, and it could never satisfy that. Therefore, the theta could never satisfy the permanence property that is required. That was the third principal abstraction. That was the only one relating to the inner factor. So the summary of bad behavior is as follows. We have seen the three principal ways, more or less, some of them qualitative, some of them a little more geometric. But the carrier set of the weight delta, it could be too complicated. That was basically Khrushchev's theorem. Also, if the carrier set of delta, even if it was very good, still delta could be too small. The last, the singularities of the fact of this critical singular inner factor of B could be in wrong places. So, well, morally, if I show three conditions, so three ways in which these things are prohibited, then I should now at least show some sort of a positive result. And so what we did with Adam, we worked hard on trying to construct some family of extreme symbols B, which avoids these pre-obstructions, and for which we get these approximations. We can approximate by smooth functions. Well, we got to work on the PT mu side of things, and we proved the following theorem. So we can, if we can decompose this weight, this delta weight on the circle into pieces, it's a countable number of weights wk, and we have the following conditions on the pieces. So the weight wk, it lives on a Beurling-Carleson set ek, and therefore delta lives on a countable union of these Beurling-Carleson sets E. So in other words, qualitatively, delta lives on a good set. And moreover, these WKs are not too small. So they are locally on the EK, on the Beurling-Carleson sets that they are defined on. They are locally log integrable. So that means that WK is not too small and the delta is kind of locally not too small. And observe that this certainly defines, these conditions give us extreme symbols. For instance, if the union of the EKs does not fill out the entire unit circle. So certainly we are in the extreme case. Well, then we prove the following. First of all, MZ is completely isometric. So we are in a space of analytic functions for any alpha. And if nu is a singular measure which is carried by this union of the EKs, then the division property P does hold for this singular inner function. And this is what we need according to this to the main theorem. So it has an immediate corollary. And before I state the corollary, I also have this little picture of what I mean. So we have our measure. We have the delta weight which lives on the blue part here, and the singularities of the inner function, the one that vanishes on BC sets of measure 0. They should be placed. I mean, they should be located on the support of delta. If this is so, then the singularities will then this inner factor will be passed on, and in the norm convergence, and P property will hold. Now, immediate corollary is the following. So we give a recipe for this for a big family a recipe to construct basically an extreme symbol where these X alpha spaces are dense in HB for each alpha, and it follows the same. It follows the previous theorem. So we pick a sequence of Beurling-Carleson sets, some weights bounded by 1, which are log integrable locally on these sets, and construct the weight delta in this way, and take the outer factor of B to satisfy this relation. Then the singular inner factor, which is carried by the Beurling-Carleson sets, this does not matter, as I said. The Braske product doesn't matter either, but the critical part, the part of the measure nu, which will define the singular inner factor of B, this one should have mass placed precisely on the carrier of delta, right? As we saw in the cyclicity result, if there was a piece which, if this quantity was non-zero, then we certainly couldn't have this P property. So here we have basically a condition on the size of delta on its carrier set, and the placement of the singularities of the critical factor are placed according with our prohibitions, and then we have a positive result. So that's basically the theorems and results I wanted to present. I want to give some comments. First of all, a little annoyance in this last theorem, we have density of these X alpha spaces for each alpha, but we don't have it for their intersection. So if you take X alpha and alpha equal to 100, then you will have density of analytic functions with 90 or whatever, the 50, I don't know exactly. No derivatives extending continuously to the boundary, but we will not necessarily have density by approximations by functions which have all derivatives extending continuously. So we missed that. We don't think that we think that it's still possible We were working a bit on it. Things got technical. We think if we keep evolving this theory of PT mu spaces, especially a very interesting question is metric conditions for membership in these spaces, and then probably we can fill this in. A little more annoying is the following fact. So this alpha, this was the parameter here in this X alpha spaces and the parameter in the connecting measure. Well, does it play a significant role at all? You see, 1 second. In all those, I'm sorry for scrolling. In all those results that I presented, alpha, it was either the approximations were prohibited for all alphas, or as in the last theorem, we had approximations for each alpha. Well, then of course this begs the question whether this alpha plays a significant role at all. And well, we don't know. We know that in the corresponding results for the subclass of the Branges-Rovnyak spaces, which are model spaces, if you run the similar arguments, then you will see that alpha actually does not play a role. And if you have approximations by, say, functions which are, if you the space admits approximations by, say, functions which have one derivative extending continuously to the boundary, then you will also have approximations by A infinity. So I have not been talking about proofs here, and well, probably to a disappointment, our work and our approaches are, again, as often in this business, they are by duality arguments or other non-constructive methods. For instance, we use some identify closure by Beurling-Carleson theorems, and this is a non-constructive method as well. However, as now we're studying the smooth approximations. There's been the question has been raised whether there are we can approximate, for instance, in general, in an extreme the Branges-Rovnyak space, if there is a constructive method to find these approximants which extend continuous to the boundary. So the continuous case, so to say. In my opinion, that problem is, well, it's very difficult. I've been working hard on this constructive methods. I didn't get much at all. But now I want to say that for the smooth case, for these smooth approximations, there is a bit of some new extra tools that can play a role, and the situation is not as bad. And we think with Adam that at least portion of these results can be recovered in a constructive manner. And this is related, I will not have time to go through this, and I didn't really think of going through this, but it's related to the way how Hilbert transform and Cauchy transform works. Now, Cauchy transform and Hilbert transform, they don't preserve continuity, but they do preserve smoothness, such as, for instance, Holder classes or just being A infinity. So, and this is an extra tool that we've been using, and here are some possible theorems. Maybe this is bold, but I think at least number one is somewhat, I think we have good ideas with Adam how this can be done. And I think these are good. It's good to end with this because, well, these constructive approaches seem to be, well, they're hard to come by. And maybe we were thinking that we can start by something modest like this. Especially number one, I think if E is a Beurling-Carleson set on which such as this logarithm is locally integrable on this set, then in the consequence of our work is that there should, as a matter of fact, exist an integral formula for a function, for a smooth function in the HB space. And one can think that if, as a matter of fact, this quantity is integrable on the entire carrier set of delta, then it seems that maybe in near future we could attain some constructive proofs of the claims that I presented here in in some special cases. And by this I'm done, and I thank you for your attention.
Thank you very much. Now we have time for questions. For a question, then please just go ahead because I probably won't be able to see your raised hand.
I have. So when you presented this theorem, so you presented the three obstacles or
Yes.
And then you have the theorem. So doesn't seem to be too much missing. It's just this decomposition in the EKs, right? Or the WK.
Yeah. So basically, well, we were thinking like this.
To say that.
شما خوبی چیکار میکنی؟ نه این آخری اکسپوزه بود داره تموم میشه.
Okay.
Well,
Yeah.
so basically, it's like this. So we have these three obstructions where the carrier set can be bad, the delta can be too small, and the singularities of the inner factor. And now here somehow we think that all of the conditions we put here, they relate to those, right? That we construct a good carrier set from a union of Beurling-Carleson sets. We construct a not small weight from the logarithm integrability of these pieces.
I just wanted to say this doesn't seem to be too far from saying that if the restrictions don't apply, then I can do it. It's just the composition in WKs, which is is not so clear how you get it, but
Yeah, I agree.
Yeah, well, very nice. You know, I like it.
Thank you.
Other questions?
Hi, I have a question. So in your main theorem, so for the function theta, so when you go to your main theorem, so is it always in P2 mu?
Yes. So I think you mean, let's see, where is this one? This one?
Your main theorem.
Okay, so that depends on the
one.
definition.
So so for the inner function theta, so is it always in P2 mu?
Yes, PT mu is, so this is a space of, so this is a bounded function, so you can approximate it by a Thayer means or something like that, and it will appear as an inner function.
Okay, I get it. Yeah. Thank you. Sorry again. So you need the condition that the operator MZ is completely non-asymmetric, then you can approximate the inner function theta. Right? Okay, yeah.
Yes, precisely. So for smooth approximations, this PT mu space, it has to be a space of analytic functions, right? But then it has to have something more. Something has to be satisfied by the inner factor of B.
Yeah, thank you.
Other questions? Comments? If not, then let's thank our speaker again. Thank you very much. And we'll